Welcome to the second part of this first chapter that we're talking about. Today we're going to be looking at the difference between scientific laws and scientific theories, because they are incredibly different when you get down to the specific definition of each. So a scientific law describes a process in nature that can be tested by repeated experiments. So pretty much scientific law predicts what will happen. So a law allows predictions to be made about how a system will behave under a wide range of conditions. Okay, so it states that something will happen. So this is kind of like if you stay out all night, how are your parents going to react? Okay, they're going to be mad. So in a way, that's kind of like your own type of scientific law, that you can already predict how a system, or your parents in this case, will behave based on that set of conditions of you staying out all night. And then with a scientific theory, the theory tries to explain how that process takes place. So it explains how something happens or why it happens. So in this case, maybe it's because your parents are worried that you're dead somewhere or that you've been kidnapped or something, and so they get mad because you made them worry, so on and so forth. So hopefully that example helped. But scientific theories are always being questioned and examined. So scientific laws, they're not set in stone either, but they are generally more accepted. Scientific theories are a little bit more mutable. They're easier to change. And you don't have to scrap the entire theory. If you make a change, you can just kind of edit the theory. So a theory must explain observations clearly and consistently. If you get results that disprove a theory, or disprove at least part of a theory, then you have to go back to that theory and rework it so that it explains all of the observations. So experiments that illustrate the theory have to be repeatable. So if it happens once, it could be a coincidence. If it happens twice, you're getting better there. If it happens at least 3 times, then it's what's called statistically significant. So that means that it is expected to happen when those conditions are met. Okay. So the results of an experiment have to be predictable using the theory. So if you remember from when you've done scientific method before, this is where the hypothesis comes in. Okay. So you have to basically predict what you think is going to happen in the experiment using the theory that you have, and then use the experiment to test that theory. So, in other words, a law is a descriptive statement or equation that will reliably predict events under certain conditions. So, a lot of times this gets called like natural law or something. It's basically like the law of gravity. If you drop something off of a table, it's going to fall. Okay, that is a reliable prediction that you can make based on the law of gravity. With a theory, this is a system of ideas that explain many related observations. So these theories can actually be relatively complex, especially if they've been modified multiple times. And it really just kind of depends on what they're trying to explain as to how complex the theory gets. So the theory always has to be supported by evidence. Better theories are supported by more evidence, so a larger body of evidence, and all of that evidence has to be acquired through scientific investigation. So a lot of people seem to think that, scientific laws are set in stone. They aren't. They're a little bit, scientists have more confidence in laws than they do in theories, but laws and theories are always being tested. So they can change based on new information. And then oftentimes you will see theories or laws that have what are called models involved. So a scientific model is just a representation of an object or event that can be studied to understand the real object or event. So there are a wide range of different models. We have models up in the classroom, like the posters that I have around the room that show like the galaxies, or even the periodic table is a model. Also, my giant microbes would be considered a model, as they represent the actual microbes that are too small for us to see, and then they're just blown up and made cuter, I guess you could say, just because. So sometimes models will represent things that are too small to see easily, or too big, or even too complex to study easily. So with the example of the too small, that's with the giant microbes that I have. And then too big, you could talk about the galaxies, the posters that I have of the galaxies. Too complex, generally when we get into that, a lot of times it's something like the cell, because there is a lot that goes on inside a single cell, and it can be too complex and too much to try to study it all at once. So instead you kind of break it down into little pieces and say study this function of the cell, and then you can study this other function and how it connects, and you build on top of it. But you use different models and images and constructions and things like that to help you study that. So oftentimes you'll see computer-generated models of molecules. So like here we have an example of the water molecule. This is a space-filling model. So it shows your oxygen atom here and how much space it takes up, especially compared to the two hydrogen molecules here, hydrogen atoms. So together they can actually form this water molecule, those three atoms together. And then when the water molecules get together, they can actually be arranged into various different patterns. And we know many of those patterns as snowflakes. Okay, so again, this is an image of an actual snowflake, but it is also considered a model because it's a little bit too small to see with your naked eye very clearly, so it's kind of a model that helps you study snowflakes. So one thing that's really important to remember about science is that it's not just the facts. Okay, it's not just like a giant textbook that has all of these random facts in it that we know about nature. It's actually using facts and known material to expand human knowledge. Okay, you don't necessarily see that until you get to the higher levels of science, or at least see that very clearly, or hands-on way, but the core of science is about increasing human knowledge and using that knowledge to improve human life. So this is another thing that a lot of people kind of get tripped up on. A scientific theory can never be proven absolutely, okay? At least not where science is right now. It's possible that it could get there in the future, but we're nowhere close to being able to prove a scientific theory absolutely. So you can have a high level of confidence in a theory, but there's always that chance, no matter how small, that that theory could get disproven or replaced or even modified in different ways. Okay? So, for example, this was actually several years ago, but scientists have recently shown that even one of the most famous theories in all of science, Einstein's theory of relativity, is not completely correct. Okay? I mean, granted, it's, as far as they can tell, it's mostly correct, but there is still that little bit that they are modifying. So going back to scientific models, these models come in three basic forms. So you have drawings, okay? Used to be that they were all done on paper. Think like Leonardo da Vinci and his drawings of human anatomy and things like that. Nowadays, a lot of times they are computer generated, or they're images of an actual thing, or they are taken with like a microscope or a telescope or something like that. You also can have physical objects, so this is talking about like if you have a model of the solar system or the giant microbes that I have, or say a model of DNA. And then this one is one that you won't see as much, but it's like a mental picture or a set of rules. Okay, so it just kind of helps you think through something in science. So scientific models, you might think that you don't really see them except in the science classroom, but you can actually find them everywhere. You'll see I've got a couple other videos up for this section that deal with some of the more common models that you see. Weather forecasts is actually a really big one that you may not pay attention to all that much, but it is very important to our daily lives. So weather forecasts, maps are another one. You might not necessarily think about it, but it is maps and cartography is actually included in oh my gosh, in like, it's not geography, and I cannot remember the other word, but earth science basically. And then of course models of the universe, so we already talked about that a little bit. So when we talk about the scientific method, again, this is just kind of a process of thinking through a question in science. So you have to identify your problem first, or your question, and then plan an experiment that would answer that question. Now, the planning actually can take longer than the experiment itself. It depends on how complex the issue you're trying to answer is. There is a lot that goes into planning experiments. Again, we're not going to get into that too much in this class just because it's pretty advanced part of science, and you got to twist your mind around a lot in order to really kind of try to think about everything in an experiment. But once you start actually doing the experiment, you do have to record your observations, and then you also have to correctly report your data. One of the biggest things in science, one of my biggest pet peeves in science, is when people falsify their data, and it just drives me crazy. But so another way of thinking about the scientific method is just, it's kind of a way of breaking down critical thinking skills. So it's a way of approaching a problem by asking a question and then trying to answer that question using logic. So again, scientific method, just a general way to organize and approach your thinking about a question that you have. You will also deal with a lot of variables. So variables are factors that can change in an experiment. Generally, you try to keep all of your variables except for one constant so that they are not allowed to change. That way, when something happens, when you get a result, you can say that it's because of the change that you did in the experiment. Variables include anything from temperature, humidity, time, colors, anything like that. So again, try to control the variables that can affect the outcome. And this can be relatively difficult to try to control all of the variables except for one. And this is where a lot of that planning of the experiment comes in. So this is just a breakdown of the scientific method. I'm sure you've seen this before. The one thing that I really want you to take from this is that it's not just a straight thing. You don't go from observation all the way down to draw conclusions. Okay? You will modify your hypothesis and then keep modifying your experiment until you feel that you have answered the question fully. So scientific tools, centuries ago, actually I'm about to run out of time, so this will be on another video. So